So today we have with us Fiona Louise Guinan. Fiona graduated from University College Dublin in Ireland with a Bachelor of Science in Agriculture Science in 2018. Shortly after, Fiona came to the United States and did an internship with the Council on Dairy Cattle Breeding in Bowie, Maryland, where she worked on national performance metrics for herds participating in milk recording programs. In 2020, Fiona started her Master's of Science in Quantitative Genetics at the University of Georgia under the supervision of Dr. Daniela Larenko. Her master's focused on analyzing changes in genetic and phenotypic trends in U.S. dairy cattle following the implementation of genomic selection. In 2022, Fiona was awarded a fellowship from CDCB and the National Dairy Herd Information Association for her PhD in dairy genetics at the University of Wisconsin-Madison. She works with Dr. Kent Weigel and Dr. Francisco Pena-Garicano to investigate resilience indicators in U.S. dairy cattle using daily milk weights routinely collected on farms. Fiona was the treasurer and is currently the president of the UW-Madison Animal Science Graduate Student Association. So thank you for joining us, Fiona. I'll give the floor over to you now.
Thank you very much for the introduction. And I'd like to say thanks for the invitation to talk here today. I'm very excited to show you or to talk about the first project in my PhD thesis and some of the objectives and where we are going to go next with this work on resilience. And so, yeah, I'm excited to get some questions at the end and hear your input as well. So the topic of the talk today is the genetic analysis of lactation consistency in US Holsteins using temporal variation in daily milk weight. And I guess to get started, let me just check here to make sure here we go. Okay. So I guess the first component of this presentation will talk about consistency, and initially the first step will be calculating consistency indicators, and I'll be explaining, as I have here, why consistency is key, how consistency relates to dairy cattle production, and then how we can move into resilience indicators. So as I mentioned, resilience is the topic of my PhD, and we all are aware that it's a complex trait. And so the first step was to simplify it into consistency. And I'll show you some results that we just published in the Journal of Dairy Science on this paper on consistency, and then some of the ideas we have for resilience indicators. As well as that, a novelty of our data set. So we have a national data set representing US cows and dairy cattle. And we have the pen information, so we know where each cow was on a given day. And this can be very valuable when we start to think about resilience indicators and how cows respond to different challenges, not only at the herd level, but also at the pen level. And then finally, I'll talk about some conclusions and next steps. As I mentioned, we're still, I'm about just over halfway through my PhD. So we have the first paper complete, but there's still plenty of work left to do, and we have lots of data to carry out this work. So I guess one of the interesting ideas with this work is, and it's a bit ironic actually, is how do we identify this anonymous cow? So the idea of the anonymous cow, it's this cow that, you know, has such few issues throughout the lactation. They just keep trucking along. The producer doesn't even know the cow's ID because she has such few problems throughout the lactation. And therefore, some of the terms or the definitions used to describe such a cow is resilience and robustness, but also this trouble-free cow, which is more labor efficient. And why is she more labor efficient? Well, because there's less movements required for the cow. So for example, many herds have the different pens, for example, like the sick pen. And so if this cow is just consistently performing throughout the lactation, she's really not moving pens, or we like to call it going on holidays from pen to pen throughout the lactation. And I have some examples on this, but I believe this is very valuable for producers, not only for genetic selection of these animals, but also for management. In terms of consistency, phenotypes, farmers can manage their herds differently and manage animals differently based on the pen level, at the pen level as well. And so keeping this idea in mind, I'll talk about how consistency phenotypes can help us to identify these anonymous cows and where the value is in terms of labor efficiency for producers in the US. I guess another important first step here is, what is consistency? And I'm sure many of you have an idea of consistency in your a definition that you're familiar with. And so the actual definition from Oxford University Press is a level of performance that does not vary greatly in quality over time. And so our goal with measuring consistency is to achieve predictable performance in unpredictable conditions. And when we think about unpredictable conditions, what we're referring to here is increased environmental variability over time, which includes extreme weather events. So in the case, because we have a national data set, we're able to capture these extreme weather events, but historically these only occurred in the southeast, let's say, for example, like the states of Florida and Georgia. However, we know, at least for us in Wisconsin, back in August, we had an extreme heat about the last week in August or so. It was like 100 Fahrenheit or so. And so these events are increasing in frequency over time across different areas. This also includes variability in labor availability. So, for example, there's a labor shortage for agriculture in the US because of competing markets and so on, and location of farms as well. It can be challenging to find people, and so as a result, finding these cows that require less attention and are more consistent or resilient can be very beneficial economically for producers. As well as that, we have variability in nutrition as well. So, for example, bad feed at certain points in the year because of weather events or so on throughout the year. And so, can we identify these cows that can consistently produce milk as expected despite these challenges and variability? And in thinking about cows and, really achieving predictable performance in unpredictable conditions can be related across different sectors. So we can think of this in terms of employee performance, but also we can think of it in the context of athlete performance. And so, I was thinking about how we can manage cows, similar, like a herd of cows, similar to a soccer team, for example. And so that leads us into the example I have here that will hopefully lay the foundation for how we define consistency, classify consistent performance based on the phenotype that we have calculated. And so I was thinking about this in terms of athlete performance, and I included the example of hurling here. So I don't know if my accent gives it away or not, but I'm not originally from Wisconsin. I'm from Ireland, actually. And in Ireland, we have the national sport of hurling. So hurling is a mixture of field hockey and lacrosse, and maybe some rugby thrown in there too. But I play on the female version, which is camogie in Madison, and I played in Baltimore before. And I was thinking about consistent performers and how reliable they are and how little attention they require in terms of when you're putting a team together. One of the reasons I picked hurling also is because on the fourth floor here, we have a lot of people from South America. And so when I looked up the most consistent athletes, it was Messi that popped up. And so I wanted to avoid some controversy within the department here when I presented this. But anyway, so we have player one here, which is Joe Cannon from County Galway. And so he scores on average 4 goals per game, which is pretty high in terms of a hurling game. And so what's interesting though about Joe's performance is that once we start to break it down, depending on the opposition team level, it's highly variable. So we can see here we have a less challenging game. Joe scores 9 goals, which is great. However, once we go to a challenging game, that drops down to 2. And in a very challenging game, it's 1 goal. And so although the overall average is 4, when we start to break it down, depending on the challenge that's presented, his performance is highly variable. Now, for player 2, we have TJ Reid here, who's from Kilkenny, and he has a 3-goal average. And so we can acknowledge that it's slightly lower than Joe's. However, once we start to break it down and look at the opposition team level, we have less challenging, and very challenging. And regardless of how difficult the opposition team level is, the number of goals remains the same. And so in thinking of putting a team together, from my perspective, I would absolutely choose TJ every time, because I know regardless of the challenge that's presented, he's going to score 3 goals every game. And so with that, then our definition, our classification here is inconsistent. So we have an inconsistent player here on the left, Joe, because of the level of variability in his performance. And on the right, we have a consistent player. And so as we move through the presentation, I'm going to explain how this relates to dairy cows and how we can identify those inconsistent and consistent performers, and how we can utilize that moving forward in terms of improving resilience and sustainability of dairy farms. And so our data is a monster, I guess is one way to describe it. It comes from the Dairy Records Management Systems, DRMS, which is a dairy records processing center in the US. So we have 4. And I'd like to just take this moment to thank Robert Fordrain for his collaboration on this project, for helping us to apply quality control to these new data sources and helping us to understand exactly what the variables mean and so on. It's been incredibly informative and helpful for the analysis. And so the data set that we have here is we currently have 333 million individual daily milk weights, and these daily milk weights come directly from the farm. So it comes from the PC Dart software. And so they have a 90-day backup of the files. So when I started my PhD, Robert shared the data 3 months back for the daily milk weight, so for every individual daily milk weight. And then he was able to retrieve the historical aggregated daily milk weights prior to the 3 months, the 90 days. And so we have 82 million historical aggregated daily milk weights, which is the sum of the daily milk weight per day. And these data come from robotic and inline milk meters. Along with this new data source, we have the traditional test day records. So we have that are collected by the DHI system. So the National Dairy Herd Information Association oversees this, field service affiliates, and so on. So these data go through quality control. So we have 22 million test day records, 4.4 million health records, and 2.6 million breeding records. And once we start to dig into resilience and resilience indicators, the health records and the breeding records become very important. So we can identify when a perturbation occurred and how that affects the cow's resilience on an individual level, but also on a group level, because we have the pen information. So finally, then, this represents 311 herds in 37 states across the US. And we have 528,000 cows now. And this database is continually appended. And so every month, Robert shares the data files, which we append to the database to build our lactations. So I just have the first step in this project was to build this data lake, and we use the SQLite package in R. And so we have this DRMS database, I called it. And on the left-hand side here, I'm considering the traditional data that we currently collect for majority. We currently collect for genetic evaluations in the US. So calling this test day traditional data. And so this includes ID and test day, lactation information, breeding data, and health data. We also have the genetic and genomic PTAs. And finally, another data source is that we have the vet check data and the sick pen data. Now, I haven't explored this yet, but again, I do think it'll be very valuable for resilience indicators later on in our analysis. Then on the right-hand side of this, we have the daily milk weights. And again, I mentioned we have historical and daily milk weights, which are, the historical are the aggregated, so the sum of the milk weights, and then the daily is each individual daily milk weight. So I have a graph or a map here, a plot, to show how these cows are distributed. And so what you can see here are the number of cows per state. So with records for either lactation 1, 2, and or 3. And you can see we have a very good distribution of cows across the US. And you can see mainly it's on the East Coast. This is because the Dairy Records Processing Center, DRMS, there used to be more regional. And so before DRPCs combined, they traditionally catered to the herds on the East Coast. But you can see this is growing, and this is great for our analysis because we have many different geographical regions represented. So for example, we have about 25,000 cows in Florida, about 35,000 in Pennsylvania. I'm really testing my geographical knowledge now of the US states, but we have Michigan over 30,000 cows, and then for Wisconsin, we have between 20,000 and 30,000 cows. But when we start to think about individual responses to different weather events, having the data in Texas, the likes of Texas as well, is very valuable. And then, of course, the grey states represent areas with no available data. So moving on then into the data edits. And so we have two data sets. These are the edits that were applied to both. The first data set relates to the univariate analysis that we did. So for that analysis, we have lactation 1 cows only. And then for the second analysis, we did a bivariate analysis for a multiple trait model. And we had lactation 1, 2, and 3, and or 3 for that analysis. But these edits were applied to both data sets. So to begin with, we restricted the recorded breed code to Holstein. They represented 90% of the data, so we decided to start there. And of course, this can be extended to other breeds and other edits moving forward, but we had to start somewhere, and this is how we decided to begin the project. So we started with Holstein cows that were milked 3 times a day. We did remove the automatic milking systems. These represented 10% of the data set, and so to avoid the challenge of the milking system effect, we decided to just start with inline milk meters. And so again, we can go back, but we will need to edit the data slightly different in order, in relation to assigning milkings to different days. So for example, if a milking falls between 12 a.m., if half the milking is before 12 a.m. and half is after, we can adjust records accordingly. We removed estimated records. So what's interesting is if there's an ID error on the farm or there's some problem, a lot of records are interpolated. So they will be, I'm not exactly sure because there's different software that does this, but the nice thing about our data set is that we were able to identify records that were estimated. And when we plot lactation curves, we could easily identify estimated records because they didn't follow the biological lactation curve that we expect. We also removed outliers, and so we use a package in R called Forecast and the TS Clean function, where we removed the seasonality and the trend in the lactation curve for a cow, and then found the outliers in the remaining series, which was outside three times outside the interquartile range. We limited days of milk from 5 to 305, and then they had to have at least 100 daily milk weights per lactation, and restricted milkings from 2018 to 2023. So after these edits were applied, the final data set included 21.8 million observations from 102,000 cows from 213 herds in 30 states. And then for the multiple trait model, our final data set with parity 1, 2, and 3 cows included 51.4 million observations, daily milk weights from 255,000 cows from 222 herds in 32 states. And so I'll start here with the first step. How do we measure consistency using daily milk weights? So we had to calculate our phenotype first, which we called temporal variation. And so we used 3 different methods to model the lactation curves using the daily milk weights. And the first one, these are the same cow using 3 different lactation curve fitting methods. And so we have days in milk here on the x-axis and daily milk weight on the y-axis. And so the first method that we used was a non-parametric method, loess regression, with a span of 0.75. And loess regression focuses on fitting a smooth curve to the data. locally weighted regression is used to give more importance to nearby data points. And then it considers a small neighborhood around each point, and the weights decrease as you move further away. So we'd consider 75% of the neighborhood around the point that we're trying to predict. For quantile regression, these are both examples of quantile regression. One is with a 0.5 quantile, which is the median, and then we use a 0.7 quantile. And so along with a fourth order polynomial to fit the lactation curve, the expected lactation curve. And so the gray dots are the actual, and then the lines through, the smoothed lines, are the expected. And so we can see just a slightly different curve to the low S, and similarly for the 0.7. We use 0.7 to test similar work that was initially done by Poppy in the Netherlands, where they considered the 0.7 quantile to be the phenotypic potential of the animal in the absence of any disturbances. So you can see it's the exact same curve, it's just shifted slightly upwards. And so after calculating the expected line, our phenotype was TEMFAR, temporal variation in daily milk weights, and it was the actual yield minus the expected yield, and we log transformed the variance of the yield minus the expected yield to account for the non-constant variance throughout the lactation period. I have some examples here of, two cows, a consistent cow and then an inconsistent cow. And these two cows come from the same herd, similar calving dates, first parity cows. So we wanted to account for these effects to ensure we're comparing like with like. And so we have the days of milk on the x-axis and daily milk weight on the y-axis. And I just used the quantile regression 0.5 with the fourth order polynomial to plot the predicted line here. And the black dots represent the the actual daily milk weights. And so what you can see here is that the black dots are tightly aligned with the expected. And so because of this, we have very little variation over the lactation period. And so the phenotype for this animal is 2.86. Now, when we go to this inconsistent cow, I'm sure you can notice the obvious difference here. But again, we have days of milk on the x-axis and daily milk weight on the y-axis. And our predicted line here in blue, the quantile regression of 0.5. And so we can see a ton of variation throughout the lactation period. But also we have two clear perturbations here. So one is just before day 100 in milk, and another one happens shortly after at day 120 or so. So as we move more into resilience, we're more interested in these perturbations and how cows recover from such perturbations. But for now, our phenotype measures the entire variation over the lactation period. And so for this cow, we have a TEMFAR of 4.68, which is almost double the previous cow. And so the idea then is that consistency is the total variance over a lactation. Less variation is equal to more consistency, and more variation is inconsistency. And so we use an animal model for our univariate analysis to calculate the genetic parameters of TEMFAR. And so our fixed effects were age at first calving. Because this is first parity, we had 6 levels. We used herd year season as a fixed effect, and then we had random effect of cow. And we modeled the relationships among animals using the pedigree data, which went back 5 generations, which we retrieved from CDCB. And so we looked at the heritabilities of each lactation modeling method. So for low S, we had a heritability of 0.237 with a standard error of 0.01. For quantile regression with the 0.5 quantile, we had a heritability of 0.231 and a standard error of 0.01. And then again, for the 0.7 quantile, we had a heritability of 0.227 and similar standard errors. So what this is telling us really is that despite the lactation modeling method used, we're still capturing the same trait, which is the temporal variation in milk production throughout the lactation. And then our interpretation of the phenotype, we can classify it as either consistent or inconsistent. We also looked at estimated the sire PTA correlations with TEMFAR. We did this using the Callow method, where the Pearson correlation is corrected for the accuracy. And so we retrieved the sire PTAs from the Council on Dairy Cattle Breeding April 23 evaluation run. And so the TEMFAR phenotype, so a higher value for TEMFAR means more variation, and therefore we have a positive for 0.57 positive correlation with milk, which indicates as milk increases, so does TEMFAR, so more variability, which makes sense because of the relationship between mean and variance. So as the mean increases, so does the variance. However, this value isn't high enough in order to correct for the milk yield. And also we don't do that for other traits. So if we do implement this, the idea is that we wouldn't correct for milk yield. Somatic cell score, this is desirable. So I'll just interpret this. So somatic cell score represents the genetic susceptibility for udder health. And so as TEMFAR increases, so does the PTA for somatic cell score, which is undesirable. So therefore, we want a low PTA for TEMFAR and low PTA for somatic cell score. For productive life represents the expected to remain in the milking herd before removal by culling or death for cows. And so higher variation PTAs lead to lower productive life PTAs, similarly for livability. And again, for our fertility measure, which is daughter pregnancy rate, more inconsistent cows tend to have lower PTAs for daughter pregnancy rate. And so we have all of the traits included in the paper that's published. So if you're interested, you can find them there. And we also calculated the correlations with early postpartum health traits. These range from -0.41 to -0.08, and therefore more consistent cows tend to have fewer health problems. I mentioned we did the multiple trait model, and really with this we were interested in learning if consistency was the same trait throughout lactations. And so here we have a similar model, except calving age is nested within parities. So we have 6 levels per parity. And then again, we have the random effect of cow, using pedigree information to model these relationships among animals. And what we were interested here is that if we select for consistency in first lactation, are the same genes affected in lactation 2 and 3? And the answer is yes. So what we found is that the genetic correlations between lactations for consistency for TEMFAR were all above 0.96. And so it's very close to 1. So we're 0.96 genetic correlation between, at least a 0.96 genetic correlation between parities for TEMFAR. We were also interested in calculating TEMFAR, the heritabilities of TEMFAR in different lactation stages. And so following the feed efficiency work, we decided to break the lactation into 3 stages. Well, basically around the mid-lactation stage. And so we have day 5 to 50 days of milk for the first lactation stage. We have day 51 to 200 in milk for the second lactation stage. And then day 201 to 305 for the late lactation stage. And so what we found here was that we have some phenotypic measures here of TEMFAR throughout the different lactation stages. We also have the additive and the residual variances along with the heritabilities. And so what we expected was that the heritability would be higher in the mid-lactation stage because of the decreased environmental variance. And we expected it to be lowest in the early lactation stage and then somewhere in the middle for the late lactation stage. And what we found this, so the heritability in the first lactation stage was 0.154, probably because of the increased environmental variance during this time, during the transition period. But what was interesting here, what I found most interesting is that the additive variance during the early lactation stage was highest. And I just showed low S here. I did have quantile regression 0.5 and 0.7, but it's a bit overwhelming, the amount of numbers. So for simplicity, this is just log transform variance of low S. We can see that the additive variance is highest or comparable with the mid-lactation, which indicates that in challenging conditions, resilience is expressed, which has been found in other papers as well. And so when we can really identify resilience in the first stage of lactation, even though the heritability is lower and the environmental variance is higher. And then in the mid-lactation stage, we had a higher heritability. You know, the cow's job here is to increase intake and increase milk production, and once they've gotten past the first lactation stage, this is their job during this stage, and so the heritability is higher. And then finally, we had a slightly lower heritability in the final lactation stage, probably because energy is being diverted towards developing the fetus, and so there's an slightly increased environmental variance. So that's what I have for consistency, and now I'm going to move into resilience. And I want to be very clear about the differences between consistency and resilience, because I know it can be slightly confusing. So the definition of resilience that's used regularly is their most popular definition is the capacity to bounce back to normal functioning after a perturbation or maintain specific functions in the face of change or stress. And this comes from a very concise paper by Scheffer et al. In 2018, where they look at different resilience indicators across species as well, and within the context of agriculture to define what resilience is, and some suggestions on how we can measure it, not just only from the quantitative side, but also the physiological aspect of resilience. And so how do we currently measure resilience? So one of the things that differs between resilience and consistency is that in order to be resilient, or to understand resilience, we have to have a perturbation occur, and then we need to understand how animals respond to this perturbation. So I have a couple of examples here how resilience is currently calculated. This is work from the Netherlands by Poppy, where they calculate resilience indicators, which we similarly calculated and considered consistency. So you have the log transform variance of the daily milk weights over time, and they found the heritability to range between 0.198 and 0.244. So what's interesting here is that, again, I think it's a simplification of resilience, and it's a practical way to implement resilience. However, we haven't identified a perturbation and understood how cows respond to that yet at this stage. Secondly, we have a paper from Wang et al. In 2022, where they have an expected lactation curve here in red, and then the actual milk production in the black dots. And so they were interested in, we can see the different points of the perturbation here. So A is when the perturbation started, B is the end, and then C is the minimum point. And so they considered a perturbation to be a milk fluctuation with a period of at least 10 days, where one of the milk yield observations dropped at least 90% of the expected. And so they investigate different milk loss traits, such as the number of milk loss events, the duration within lactation, the percentage of milk loss to milk yield 305. And they found heritabilities ranging from 0.004 to 0.061. So again, to compare these two, there's a big difference in the heritabilities. However, I believe we're getting closer to resilience indicators once we start to look at this recovery as opposed to the total variation over time. And then finally, this year, a paper was published by Chen et al. A couple of months back in 2023. They used genomic parameters to calculate resilience indicators such as WF-PERT, which is the weighted occurrence frequency of yield perturbations, and also the accumulated milk losses of yield perturbations, these DPERT. And again, the heritabilities were much lower for these traits, so they range from 0.01 to 0.06. And the authors conclude that perhaps we need a combination of these different resilience indicators to ensure we're capturing actual resilience when we're measuring the heritabilities. And so in terms of our analysis then, I mentioned before that we have this pen information for the cows at the beginning. So we have each pen is identified for each daily milk weight. And again, I have this consistent cow with a TEMFAR of 2.86, and I've identified her pens. So she was in 3 different pens throughout her lactation. And so our hypothesis then is that consistent cows don't change pens as much as inconsistent cows within a lactation. Now, obviously, this is within a herd as well, because different herds have different management strategies. But the idea is that cows that are consistent, they're not being moved around as much because they're not having to go to the sick pen or being moved to different pens for different management strategies. Also, they don't have as much milk loss as a result. And so I have this inconsistent cow shown again, and her temp var, just as a reminder, is 4.68. And so what's interesting about this cow now, once we identified the pens, this cow was on a ton of holidays throughout the year. And so before day 100, we have this clear perturbation, and she moved pens here. And then after day 100, she had another perturbation, and it was much more extreme. It took longer to recover from, and maybe that's a result, an effect of having one previous perturbation before. We can also investigate this. But she was in 8 different pens throughout her lactation. And so some of the questions we're currently looking into are, can group demographics provide additional information for resilience indicators? And so how to utilize this information. So for example, this specific perturbation, it could have been caused by extreme heat events or cold events in Wisconsin, or by different management factors such as labor shortages, or there could have been an infection throughout the herd that affected all the cows, or maybe just the cows within this pen. And so what we want to find out is, were all the cows in the pen affected by the perturbation? And so we can look at the perturbation on a pen level, but then we can look at the individual responses to the perturbation and capture resilience in this way. And then also, how are cows moved pens based on changes in production? So for example, the sick pen. So this is where we can pull in the sick pen data to identify which pen is the sick pen, and then figure out how to create these contemporary groups that are not just at the herd level, but also at the pen level. And so I have one graph left here on the correlation between the total number of pen moves per cow per lactation and their temp var phenotypes within the herd. And so what's interesting here is that we found 75% of herds had a positive correlation. So what does this tell us is that the more within a herd, obviously, again, because different herds have different management strategies, but the more pen moves that a cow has, the more inconsistent they are. And 75% of these herds, I believe it was 230 after edits, had a positive correlation within the herd between the number of pen movements and the temp var phenotype. So more pen moves were more inconsistent cows. And so we're working now to characterize herds based on their pen management strategies. And then once we understand these different characteristics, we can start to capitalize on this information for calculating resilience indicators. And so I have some take-home messages, and consistency indicators are heritable. So they range from 0.231 to 0.237. And we had similar results regardless of the lactation fitting curve that was used. Also, consistent cows have fewer health problems and increased longevity. So again, these trouble-free anonymous cows are very desirable from an economic perspective and from a labor perspective. And also, they have less milk loss because they're not being treated as often, and the milk can flow into the tank. And then finally, group demographics are useful for understanding consistency and resilience indicators. And as I mentioned, we're currently working through this massive data set to figure out the trends in management strategy for grouping cows, and then how that's recorded. And so once we do that, we can capture the individual response on a pen level perturbation. So with that, I'd like to say thank you very much to my advisor, Kent Weigel, and my co-advisor, Francisco Pena-Garicano. Again, to Robert Fordrain for the collaboration with the data. And I'd also like to thank the Council on Dairy Cattle Breeding and the National Dairy Herd Information Association for the funding for this PhD fellowship. And finally, I'll take any questions that you have. Thanks very much again for your attention and the opportunity to present here today.
Great. Thank you, Fiona. Yeah, we'll open the floor to questions. I already see a couple here. Let's start with Bayodi. Go ahead.
Hello, can you hear me?
Yes.
Yeah, thank you so much for the question, for the presentation. So I'd like to know, is there a difference between consistency and persistency?
Yes, that's a great question. And so Persistency is measuring the slope after the peak of milk yield throughout the lactation. And so that's really the decline in milk yield after the peak is reached, whereas we're measuring the total variability throughout the lactation. So that would be the difference between persistency and consistency.
Right. So did you try to look at consistent animals if they were also persistent?
So no, we didn't look at persistency, actually. We just focused on the consistency as a measure of resilience.
Okay.
But it could be interesting to investigate the relationship between the two.
Right, yeah, thank you.
Thank you.
Colin?
Thank you, Fiona. So I was just thinking about for those correlations, they all look pretty good, or what you'd want, bar milk. So I was just kind of wondering, was it milk yield that you looked at, or did you look at the components within milk itself? Because it's not necessarily a bad thing if yield goes down once the components themselves are still staying high.
Yeah, that's a great question. So because the correlation between milk yield and fat is like 0.4, we found fat, off the top of my head, I think it's like 0.45 or between 0.45 and 0.5. So it is slightly undesirable, but it's 0.5, which means it's not for all of the animals in our data set right now. So I think we have some room to still select for consistency. We may have the case where we have slightly lower producing cows, but they're more consistent, which could be, I mean, I'm interested in doing an economic analysis on that to see if having a consistent cow where you have to calculate the labor efficiency, that's decreased labor, and also the amount of milk loss, because if the animals are consistently or regularly in and out of the sick pen, there's going to be a lot more milk loss as well. So the question is how much the milk is actually making it into the tank, even though they're a relatively high performing cow or producing cow.
Very cool. Thanks, Fiona.
Thanks, Colin.
Okay, we have a question in the chat. I can read it out. I can imagine that lactation consistency, resilience, and robustness can be important for farmers, but has anybody tried to calculate their possible economic importances? From the proposed definitions and examples, it's hard to imagine what could be the size of variation of the trait and, in consequence, how much we can gain from selection.
Yeah, thank you, Thomas, for the question. So I touched on that in my answer to Colin, but I think the perspective that we're taking on this is labor efficiency. And so with the increase in herd size for dairy farms in the US and the decrease in labor availability, I think having consistent cows where you don't have to worry about the cow's ID because you have such few issues, there is an economic advantage there. However, as I mentioned, we do have to calculate that, and I'm interested in calculating that. But we need to first understand resilience as well and how the two work together, and then combine the two to measure the economic aspect of it as well.
Okay, and Flavia?
Okay. Hi, Fiona. Thank you for the presentation. Really, really nice, clear. I really enjoy it. I have a question for you. If you imagine like there is a cow with no perturbation, okay? When you look at the variation, temporal variation of milk production, it is quite similar with the variation in feed intake, daily feed intake. So do you know how the daily feed intake would relate with those fluctuations of milk production? Have you looked at this?
So that's a great question. And I think it's an upstream process, right? So the variation in milk production definitely depends on the variation in feed intake. And so my colleague, Leisha Cavani, is a postdoc here at UW. Leisha has investigated the consistency in dry matter intake using the feed efficiency data. And so she found a correlation, I believe, of 0.6 between the consistency in dry matter intake and the consistency in daily milk production. Again, that's in the period between 50 to 200 days of milk. And I think that's very important. However, we don't have that data on a national scale. So to be able to calculate this using data that's being currently used for management purposes, but not exploited for genetic selection, I think it's very valuable from that aspect. But yeah, I definitely agree that it's very dependent on the intake.
Yeah. No, I asked this, I have the feeling, I remember the literature, because to understand what's behind the fluctuation, right? And then it could have different approaches to trying to reduce this fluctuation of these highly producing cows.
Right, and yeah, and one of the ways we're going to, it's kind of a validation, but I would like to utilize the fact that we know that there was a heat stress event in Wisconsin at the end of August, and so we can investigate some Wisconsin herds, the pen level responses to that. And we could validate it with the UW herd as well, because we have the daily milk weights to understand that relationship when an actual perturbation occurs. So it's adding like another level to capture resilience. You know, and obviously we have data on the herd too, when pathogens or infections affected certain pens. So as we start to combine all these data, I think we're going to get closer to true resilience.
Thanks, Fiona. Very interesting stuff.
Thanks very much.
Flavio. Do we have any other questions in the audience? I was wondering, just when you use such large data sets, I'm always interested in kind of like standardization of your traits and how to ensure kind of you're measuring the same trait in all these different farms. Is there a way that you kind of made sure to do that?
Yeah, so that was actually, we spent a long time discussing this at the beginning, because we have the two streams of data, and just being very clear on that is important, because one side goes through the DHI system, which is a legacy system that has been built over 100 years or so to provide strict quality control and ensure standardization across different testing methods and systems. And so with the daily milk weights, we spent a lot of time finding ways to ensure standardization across the milk weights. So for example, finding a robust method to predict the lactation curve is important, so it's not sensitive to the perturbations. And also outlier removal was very important, because we're not only interested in like strictly removing 3 standard deviations outside the average milk production for a herd, let's say, because we're actually interested in keeping those perturbations where a perturbation actually occurred and the milk yield decreased. So we went through a lot of rounds of finding, I actually used a package in R that's used for economic time series modeling. So we spent a lot of time on that. And then I mentioned the estimated records were removed. So plotting lactation curves was something I did a lot in the first couple of months of my PhD. And yeah, I was very conscious of that, because when we're calculating a trait over the entire lactation, using all of these records as well, I think it's very important to be accurate with that.
Yeah, that's a very large data set, so it's always fun. All right, any other questions?
If there are no serious questions, then I'm going to make a comment.
Yeah, go ahead.
Going back to your example of hurling with the two players there. So I think if to translate to soccer, the first player will be Neymar, the Brazilian player. The second player will be Messi, the Argentinian player.
Yeah,
I
so
think the statistics will be very similar distribution.
Good to know, because I know Francisco was very happy to see the second player. He had the same colors as, I guess, his team in Uruguay. I'm not very familiar with soccer, but yeah.
When you mentioned that, I immediately thought about these two soccer players.
Yeah.
Okay, it's still time for serious questions. I have a question, out of curiosity, Fiona. How far are you in your PhD program?
Yeah, so I almost 2 years. So I have in January it'll be 2 years, and then I have another year and a half to go.
Okay.
So I have lots of
plenty of time yet. But
yeah, and lots of data and lots of questions. Yeah.
but eventually you need to leave for others, no?
Exactly. Yeah, for sure. There's a lifetime of research in that database for sure.
Yeah. Very good. Excellent. Thanks, Fiona.
Thank you.
All right, so that looks like all the questions for today. Thank you, Fiona. That was a very nice presentation. And thank you everyone that joined us today. And this is the last seminar of the semester, so everyone have a nice Christmas break, and we'll see everyone back in the new year next semester. So
Thanks
thank
again.
you. Yeah,
It was
bye.
a wonderful experience. I know.
Yeah. Happy holidays, everybody.
Yeah.
You too.